You've probably seen those videos showing the scale of planets to stars ranging from M class to O class and the many supergiants we've observed when looking far into space. But what if we zoom in? Take a look at this bucket of water. When we zoom in, we see the compound H2O. And if we zoom in even further, we see the nucleus, composed of protons and neutrons orbited by electrons. Now, what if we go even further? When we smash these protons with electrons, we see they are made of even smaller particles. These subatomic particles are called quarks. There are many different types of quarks, 6 to be exact. And alongside these quarks, we've discovered many more elementary subatomic particles. One classification of these particles is so small, it stumped science for decades. So undetectable, and trillions pass through your body every second. How do we discover neutrinos? Well, in the 30s, there was a discrepancy in the missing energy of beta decay. The laws of energy conservation contradicted the scientifically accepted calculation, as there was a missing portion of energy that just vanished with beta decay. This missing piece prompted the proposition of an undetectable, untraceable particle release that takes the remaining energy from the process of beta decay. Two scientists, Cohen and Rines, conducted an experiment within the proximity of a nuclear reactor. They had large tanks of water that they utilized to see if they could recognize any reaction between the neutrinos and protons of water, an extremely rare instance. But with a reactor nearby creating these neutrinos, all they had to do was wait. Over the course of many months, they concluded there was an average of 3 neutrino reactions per hour, finding that these ghostly particles do in fact exist. However, a follow-up needs to be asked. What about Earth's atmosphere? If neutrinos were formed through the decay of particles, then the sun's rays interacting with Earth's atmosphere should produce an enormous number of neutrinos that should be detected. So, we go to the Kolar gold field mines. Calorimeters were set up to detect a very specific interaction between neutrinos and types of rock found within the mines, as the neutrinos pass through Earth. The experiment eventually proved successful, leading the way to a specific type of astronomy called neutrino astronomy. What is that? Well, our method of detecting these neutrinos has drastically improved over the past few decades. Our main source of detection is through a specific reaction between a neutrino and a chlorine isotope, resulting in radioactive argon being created. These neutrino detectors are few and far between, however, as they need total isolation from any background signal due to the very limited interactions. So, all's well and dandy, right? There have been no more issues with neutrinos. Wrong. Through these isolated neutrino detectors, the solar neutrino problem was discovered, a major discrepancy between the predicted number of neutrinos released from solar fusion and the amount present on Earth that we can detect. And the problem plagued scientists for 4 decades, up until 2002. Neutrinos have 3 different states: electron, muon, and tau. The Sun was believed to emit specifically electron neutrinos, and we were, hence, only searching for said electron neutrinos causing our discrepancy. But then, some smart scientists discovered the concept of neutrino oscillation, meaning neutrinos can change states, or flavors as they're referred to, as they travel through space. Once this was taken into account, we began searching for all neutrino types emitted from the Sun. The discrepancy, and subsequently the solar neutrino problem, was solved.